This class we will learn the physical significance of Riemann curvature tensor. So we do this by considering two particles that move in a given gravitational field such that they start off from nearby points A and A prime with the same velocity. Because they are starting off with the same velocity at point and A and A prime, they are moving with the same speed along the same direction. We will follow the trajectory of these particles and see what happens to the separation between these two trajectories. Okay, in order to do this, it is important that we choose coordinates. So let us choose x mu as the coordinate of the particle at A and x prime mu as the coordinate of the particle at A prime. Now, the analysis that we do could be made still simpler if I choose one of these two coordinates to be a freely falling coordinate. Let us choose the one at point A to be the freely falling coordinate. Now, this means that the observer using the coordinate x mu is a freely falling observer. And for such an observer, there will be no effect of the gravitational field that he will experience. We could make it still more simpler, further simpler. In fact, if we choose the speed of the particle to be the same speed of the frame in which we have the coordinate x mu to be the same as that of the particle at A. If we do that, then the particle instantaneously will be at rest at point A in the frame that uses coordinates x mu. Thus, we can write that x mu to be the time that we measure in which the particle is at rest, which is nothing but the proper time, times the speed of light. Then the coordinates of the particle, which we could choose conveniently to be the origin. Now, since we consistently work in units where C is chosen to be 1, I don't have to write this, simply write down. It is clear that the speed of the particle in this coordinate system, or the more precisely said, the forward velocity of the particle, will have the form 1, 0, 0, 0 at the point A. We could now proceed to write down the geodesic equation for each of these particles. For the particle at A in this chosen coordinates, the geodesic equation is d square x mu by d tau square equal to 0. Similarly, we could write down remember that this is the geodesic equation for the particle at A because it is written in the freely falling coordinate system. Now, if we do the same for the particle at A prime, we get d square x prime mu by d tau square equal to minus gamma mu rho sigma dx prime rho by d tau into dx prime sigma by d tau. This is the geodesic equation we write for the most general situation. We could now do the following. We could take the difference between these two equations. If we take the difference between these two equations, we get d square by d tau square of x prime mu minus x mu being equal to minus gamma mu rho sigma into dx prime rho by d tau dx prime sigma by d tau. Now, in this geodesic equation, since every quantity on the right is at point A prime with coordinate x prime, it is useful sometimes to denote this Christoffel connection with a prime so as to differentiate it from the Christoffel symbol to be used at the point A. But remember, in the coordinate x mu, the Christoffel symbol at point A is 0. That's why we have the geodesic equation with the right hand side being equal to 0 at point A. Let us now define the difference between the coordinate x prime mu and x mu to be equal to psi mu, which actually gives us the separation between these two points, these two trajectories in fact, at point A and A prime. Then we can write the same equation as d square psi mu by d tau square being equal to, on the right hand side we have minus gamma prime dx prime by d tau and dx prime by d tau. Let's now write these factors in terms of the coordinate at point A. So since gamma prime is the Christoffel symbol at point A prime, for now let me show it explicitly by writing it as a function of x prime, coordinates x prime. I could always write this as a Taylor series expansion about the point A. When I do that, I get gamma mu at rho sigma x plus derivative of gamma with respect to x nu evaluated at point A multiplied by the difference between x prime and x, which is psi nu. In this case, psi nu. And there are going to be remaining terms. Now, if I am considering the two particle trajectories to begin at a point which are infinitesimally close to each other, then the separation between these 2 points could be taken to be infinitesimally small at that point. And thus, I could stop this Taylor series expansion at the first order. Similarly, writing dx prime by d tau also using this, you see that I can write it as dx prime by d tau to be dx well, dx prime rho by d tau to be dx rho by d tau plus d psi rho by d tau. Now notice that at point A in coordinates x, the gamma at point x at point A is 0 according to this geodesic equation. Thus, the leading term in this Taylor series is 0. The next non-zero term, the first non-zero term in the Taylor series comes from the term that is proportional to psi nu. Now, if I substitute this form, since this is 0 and this is the only non-zero term, I could substitute that here. What I get is del nu gamma mu rho sigma. Now, coming to the factor of dx prime rho by d tau here, we know that the particles start off from point A and A prime with velocities that are parallel. Thus, this factor d psi rho by d tau can also be treated to be almost equal to 0 at the points where they start off. Thus, I could replace dx prime rho by d tau with simply dx rho by d tau, whose value we already know is this. Thus, I could write it as dx rho by d tau, which is nothing but in this case delta rho 0, since that's the only non-zero component. Rho equal to 0 is the only non-zero component in this. And again, for this factor I have one more, sigma delta sigma 0, in addition to the factor of psi nu coming from this. So the equation that tells us how the separation between the nearby trajectories change takes this form. Now, summing over the dummy indices of rho and sigma, it can be further written down in a simplified form as minus del nu gamma mu 0 0 sine. Now we will consider a covariant second derivative of this separation psi mu between the trajectories. So consider the covariant derivative taken with respect to the proper time of the covariant proper time derivative of psi mu. This, as we see, can be written down as now we have written the covariant derivative in coordinates x rows. Since the x rows that we have chosen are such that they are the freely falling coordinates at point A, I could now use the same fact that they have the form given here, which means that dx rho by d tau must be nothing other than delta rho 0. And thus we could write this as d by d tau of d tau psi mu plus gamma mu 0 sigma d tau psi sigma. Observe that I have already made use of the fact that dx rho by d tau is delta rho 0 and then summed over rho to obtain the second term in this expression. But whatever it is also known that such a gamma factor has all their components 0 at point A, as is seen from this geodesic equation. So we really don't have to write this term at all there. That is 0. Now let's simplify this further. By expanding out the covariant derivative, that gives us d psi mu by d tau as the first term inside the bracket and gamma mu rho sigma dx rho by d tau into psi sigma as the second term inside the brackets. Taking the derivative with respect to the proper time, we get d square psi mu by d tau square as the leading term, as the first term, and the second term involve three terms. First involving a derivative of gamma, the next involving a derivative of psi rho, d psi rho by d tau, and the third that involves a derivative of psi rho with respect to d tau. Now the second and third term, which involves derivatives of this and this factor, these two factors are multiplied by a factor of gamma. Now since this whole expression is evaluated at point A, where gamma is 0 in our chosen coordinates, the second and third term that involves derivatives of these two factors will be absent from the second term. So the only term that contributes to the second term would be the one that involves the derivative of gamma with respect to d tau. Now this derivative can further be written down as a derivative of gamma mu rho sigma with respect to coordinate x nu multiplied by dx nu by d tau into dx rho by d tau times psi sigma plus the first factor, which is d square psi mu by d tau square. Now since these velocity factors are also evaluated at point A, we know that they both must be equal to factors of Kronecker delta. So both nu and rho in this expression, the dx nu by d tau as well as dx rho by d tau will be non-zero when nu and rho are 0 each. And the non-zero value being equal to 1, we could write this expression as del mu gamma mu 0 0 times psi del 0 gamma mu 0 sigma times psi sigma plus the factor of d square psi mu by d tau square. Now we could make use of this expression for the second derivative of psi mu. Then we get del 0 gamma mu 0 0 psi psi nu minus del nu gamma mu 0 0 times psi nu. Now the factor inside the brackets could easily be recognized as the derivative, the terms involving the derivatives of gamma in the definition of the Riemann-Christoffel component are mu 0 0 nu. This is so because in our choice of coordinate x mu, the Christoffel connection components are 0 at point A. Thus, even if we had used the usual definition of R mu 0 0 nu, due to the vanishing of gamma at A, the expression would reduce to this. Now, if we had not chosen such a special choice, if we had not chosen such a special set of coordinates and worked in an arbitrary coordinates, then the same expression would have had the form R mu rho sigma nu times psi nu. But now I must take into account of the fact that dx rho by d tau and dx sigma by d tau, for which we made use of the fact that they were Kronecker deltas, they would now explicitly appear in the expression. And thus we get the form that the second covariant derivative of the separation between the trajectories have the form given in terms of the Riemann tensor. Now this clearly has a form that reminds us of Newton's equation. But for a Newton's equation, on the right hand side we would expect a force. So it is usual to term this factor on the right hand side as the tidal force. Indeed, it can be understood or interpreted as a force experienced by trajectories as they proceed in a space-time. And such a force, as shown by this expression, is proportional to the curvature of the space-time. So this is the most physically significant aspect of the Riemann curvature tensor. And this equation is often called geodesic deviation equation.